Hey everyone, my name is Jordan Rising. I am one of the founders here at Quantiscan. We wanted to take some time today and talk about what is Quantiscan. We've, or a few weeks ago, we put out a video and kind of officially announced Quantiscan, but it can still be pretty cryptic. We wanted to kind of demystify what is Quantiscan and what we're doing, and how does it compare to maybe the solutions you've used historically on the desktop or some of the other cloud-based alternatives. I could reread it, but what is Quantiscan? And it is a desktop app built with modern web technologies. This is bizarre. This is different than probably a lot of the new stuff you're seeing, which is all cloud focused. But recently in the dev world or the tech world, there's actually a movement towards local first again. And now we didn't do this to be popular. We think there's a lot of advantages here that we'll talk about, but it's a desktop app with a lot of the web technologies though. So we get the advantages of local files, local compute, local security. Your files aren't living on a cloud server somewhere in a different country or a cloud server that's just simply a long ways from you. And the speed of light is only so fast. So if you access that data in any capacity, there's a limitation to how quickly you can get and extract that data. And at its core, it's just a really good point cloud viewer. I When we started building this, I thought about my time when I was processing point clouds, and I think to myself, like, what would I hope in a point cloud viewer on my computer? Like, I don't want to have to be forced into a Windows machine or some goofy licensing or a machine with a minimum of 64 or 128 gigs of RAM. Like, those are huge roadblocks. So we wanted to tackle that. That was very important. What a huge one is for me is that you can load an LAZ of virtually any file size. Like this screen recording that I'm doing today and the demo that I'm going to do is I'm just on a MacBook. I'm not on a big server. I'm not doing anything special that the average person wouldn't be doing. We wanted to make sure that you could load data locally. We want it to be fast and secure. So, for example, if I open this is the Quantiscan app, at minimum, it's just a big Google Earth looking globe, cesium globe, which you've probably been seeing a lot of recently. If you go and drop this is a 90 megabyte LAZ, which is not huge, but if I went and dropped this into the file or into the app, it's made available immediately. Maybe a second or two. If I remove that and let's do a slightly larger one, so 400 megabytes, by the time I basically get back to the app, the whole thing is loaded. If I wanted to load a, 1.2 billion point data set, with a LAZ that's 5, 6, 10 times larger, that's not a problem. But, it's based on this file type called a COPEC LAZ. So let's just say I had an LAS now instead of an LAZ, which is basically the uncompressed version. Drop it in here. Now this one is an LAS that has no coordinate system information. So it's going to ask me to define it. I know this is California State Plane 6. And I know that this is orthometric height. So I can define those. Now it's going to convert this to the COPEC. Hopefully I'm saying that right. Sorry, Howard, if I'm not. But the COPEC file type, this is a one-time process. So once I convert this LAS to a COPEC LAZ, you can see it getting converted here. I won't have to do that again. That's a one-time conversion. And the rest of your processing chain can live as this COPEC LAZ. So it's done converting. So now if I remove this and I went and drag and dropped it, I'm not going to have to do that process again, and it's immediately available to me. But I want to compare, I think it's important to compare the two different types of apps again and discuss the architecture choices and the trade-offs between them. So up top here, you have the typical, your average web app, and then down here you have our Quantiscan app. So let's talk about a typical web app first. In a typical web app, you're opening it obviously in a browser. So you're going to Chrome, you're going to Safari, you're opening it in a browser. And for anything to show up, if you want to load a point cloud, you're going to have to ask for that data from a server somewhere, from a storage mechanism of some sort. Typically that's going to be AWS, S3. It could be It could be somewhere else. But if you want to get data there, you're going to have to upload data first, which in a typical project is quite large. There's very few projects out there that are less than gigabytes in size. Most much more than that. You have to upload to their services. Their services will then have to tile. Their services will then have to save and redistribute that data in many different ways. And then you can then ask for that data. You can ask for that data through the API. It'll come back and it'll stream those chunks back to your machine. In doing that through this API and through the cloud, there is network latency, and that's just overhead that you're going to have to pay for no matter what. Like I say right here, the data is stored in S3, or at best, it's a CDN. A CDN being kind of a more edge located storage place, which is going to be more expensive. But depending on where your location is to where your data is, it's going to take time to get to you. Again, like I said earlier, the speed of light is what it is. So you can't overcome that in any short way. The ways that they're currently trying to overcome that is, edge computing, getting more CDNs, trying to get data centers closer to people, but that is a price you're always going to have to pay. In addition to that latency, that overhead that is going to be streaming with every chunk, every bit of data, everything you do, it is expensive to store on these servers. I mean, in S3, if you're putting on a CDN, it is just egress and ingress is expensive. I mean, storage is not terribly expensive, but it adds up very quickly, especially in remote sensing. And then anything you do in addition to that, if you're classifying the data, if you're extracting it, if you're changing it, anything, you're gonna need some level of compute. And that compute isn't happening on your computer, it's happening on a server, and you're paying for that. Or your provider's paying for that, and you're paying you're paying the app provider. So, and then anytime you want to make a change, you're going to have to upload more data. That's just the cycle that these apps put you through, and it's why we have very much put our focus on a local first solution. So I'm going to divert now to Quantiscan and how that's a little bit different. It's similar in the sense that it's an app and it's got to ask for data and it's got to stream that data back. But the biggest difference is that this is all happening on your machine, on the laptop that you're using. The machine up here in the cloud app is just handling the browser. Everything else is through the API and through a server in hopefully a semi-close location. But in the Quantiscan app, everything is happening on your machine. When you request data, well, for one, there's no upload and download. So this whole ingress egress doesn't even exist. The data is already on your file system. So when you ask for data, it's going to send you back stream chunks, just the same as the cloud solution was, except for there is no network latency. There's no overhead there. And because of all this, Quantiscan works offline. If it won't stream in, like the cloud resources, like the globe here, the globe in the background, these cesium tiles, so that you can kind of mimic that. So, but it works in a sense that I'm using it right now without any background or without any globe, just fine. It's all local file system. All right, so that's kind of the high level overview of what kind of technically Quantiscan app is. We'll kind of hop into it more of a demo here. But from a viewer perspective, I mean, we've shown how you can load data types virtually instantly, but it's got full LAS 255 support, 0 to 255. So all these classes are loading in that are available in this data set. So if I view it by class, you got all your poles and wires that are well beyond ASPRS classifications. You can create schemas. So you can create a schema and say, utility XYZ, whatever utility, and they have their own schema. In the Terra Solid world, you call that a PTC. But you can load in a schema for depending on what client you're working with. So in addition to point clouds, you can load images. So you could take your drone images, drag and drop them into your projects, and I got a lot of blue going on, so it might be hard to see. Just go back to just color for now. But you can see the images as where they were taken, basic information, basic image viewer. So you have that. You can bring in ortho imagery. You can bring in vector data, so alignments, all that type of stuff. And but the oops, sorry. But the main emphasis that we've been doing originally or up until this point is on creating a digital grid, on creating a digital twin. So let's give that a shot here. Let's say demo. But when I create a new digital grid project, I have a toolkit that pops up here on the right. So we have all our add poles, add towers, if it was a transmission project, remove them, add spans, add wires, all that good stuff. But we'll start with poles. That's kind of the main place to start. I'm going to make the point size just slightly bigger. I'm going to also make this elevation, so maybe a little easier to see. But we'll start with add pole. And with the add pole tool, all you do is click somewhere on the pole and it extracts it. You know, pretty simple. I don't have to get too crazy here. It's intelligent enough to know that if I click in anywhere in this region for the most part, it finds the pole. So I have it on the extraction point called pole point, where it's expecting it to be closer to the pole, but I could also do proximity extraction, which I could click anywhere in the area. But for the sake of this, pretty dense data set, I can just do pole point. So if I click on the pole itself, it'll extract that pole. Add span, pretty straightforward. Click the two poles to define the span, and it extracts the wires. And if you've used other apps similar to this, you'll see a pretty substantial speed benefit of being local. So if I click now, 1/1000, 1.5 seconds, maybe 2. But instead of adding poles and adding spans separately, you can kind of do them as one process. So I'm going to designate this pole as a start pole here. And then every time I hold spacebar and click, it's going to create a new span and wires. So if I hold spacebar and click, span, wires, hold spacebar, click, span, wires, kind of getting to understand what I'm doing here, but in that amount of time, let's just do one more here. I'm now realizing that the elevation color kind of conflicts with the vectors, but now you can see the vectors a little better. But in that amount of time, and I was going slow, we did 9 poles, 8 spans, so it's, pretty quick, and that's kind of going at demo pace. But in that process, we're also creating cross arms. So we got cross arms there. And let's come to this pole. Let's find one with guy wire. So let's add a guy wire. It says what pole is this part of? And I say it's this pole. Add the guy wire. Snaps it to the pole, snaps it to the ground. Let's see what other. We'll do this pole. Pole, guy wire, guy wire. You can do it with one click. Just oops. You can do it with one click. It works a little better with 2. So it's guy wires. Now if we did, let's just show what like a service wire. I guess I could, just for the sake of this, make it a pole. That a pole, but we'll add a service wire. We'll make that the active pole. Oops, I just changed my active pole. That's not what I was trying to do. But, all right. Let's just pretend any of that just happened. We'll kind of set the terminating part of that wire. So we got that. As I was creating these spans, I guess I kind of forgot to do this, but I could have specified a voltage. And that would have automatically applied that voltage to these wires. But I can come in afterwards and change it anyway. So I could say, where are we? Wire settings, and let's just say that these are 69 kV. We'll click on this span, We'll show voltage. Now you can see that they're all 69 kV. I could have come in and set one separately. So let's just say I did, 120, and I clicked on this wire. Oop. Or am I going to find a bug? Early bug. Oh, there we go. I guess I need to learn how to click properly. But I can change the individual wire voltage as well, or the whole span at a time. So I know I didn't finish the entire thing here, but I could come in here now and I could import pole IDs, for example. Import pole IDs here. And I just kind of made these up. They're not real pole IDs, but you can see that the pole IDs are in the correct location here, but they're not actually applied to the poles. It's just importing them as a vector layer, basically. So I want to join those IDs to the poles. So now, after I did that, the actual poles have pole IDs. So in any subsequent logic that we do later on, you can then pull from that. And so I'm realizing how long I've been talking here, so I'll try to wrap it up. There's a tremendous amount of other functionality here that we won't have time to get into. We have macros. One of the important ones that I'll do in a different video is taking this digital grid that we made here and then classifying our data set from it. If we know where all these vectors are, we extracted this whole digital twin without any classifications. But now that we have it, we can use that to classify our data set. So it's very easy to say that, hey, here's the vector pole, take all the points around that and classify it as a pole. So that works remarkably well. And it adds all the synthetic points and pole tops, pole bottom, cross arm endpoints, all that stuff as part of that process as well. But there's a lot more macros. There's a lot more functionality to go through at some point here. But that'll have to probably be reserved for a different video here. But thank you for watching. I'll try to keep a consistent stream of these videos coming to showcase things as they come. Thanks, and have a good one.